Good morning, everyone. Today we're going to be talking about continuous probability distributions. So if you don't currently have these notes on your page, let's hit pause and get that passed out, and then we'll start today's lesson. All right, so what we're looking at today is a normal distribution. And a normal distribution has the following properties. The mean, median, and mode are all equal. And they're right here on our normal distribution. This is where our mean, median, and mode are. It is bell-shaped, and it's symmetric about the mean. So we talked about the shape of our distribution. In a normal distribution, the shape of the distribution is symmetric. The total area under the curve is equal to 1. So if we added up all these probabilities under the curve, it would add up to 100%. It approaches, but it never quite touches the x-axis. Do you see over here and over here how it's getting closer, but it doesn't quite touch it? The farther we extend from the mean, the closer it gets to the x-axis. So the closer those probabilities get to 0. The points at which the curve changes from curving upward to curving downward are called inflection points. So you should see it here. We're curving up, and at this point right here, we start to curve the other direction. Curving up, curving down. And those are called our inflection points. Our inflection points are between where we do the mean plus a standard deviation and the mean minus a standard deviation. So it's going to curve upward to the left of the mean minus a standard deviation and to the right of the mean plus a standard deviation. And it curves downwards between the two. Okay, let's take a look at, let's see, we'll come right over here and look at an example here. So if we look at these, this highest point here is our mean. So when we're looking at this one would have a mean of about, looks like it's halfway in between, so let's say 3.5. This one would have a mean at about 3.5. But this one, the highest point here, occurs at about 1.5. So we can find our mean by looking at those highest points. Now, if we go back and look at this, it says our inflection points give us plus or minus 1 standard deviation away. So the distance between here and here would represent 1 standard deviation. So let's look at this. If we look between here and here, what is this distance? Well, it goes from 3.5 to 5, so we could approximate the standard deviation at about 1.5. What is the distance between here and here? Well, let's draw that down. You might say that's 4.5. So the distance between the mean and the first inflection point is about 1. So this one would have a smaller standard deviation. And this one, let's say it looks like it's about from here to here. So we could approximate this standard deviation also at about 1. Now, does it make sense? If we look at these two curves, they look the same. That one's just shifted. So when we shift, it will change the mean. We did that earlier, but it doesn't change the standard deviation. This one, the highest point is at the same point, so it hasn't been shifted. But if we look at this one, the shape of the curve is very different. This one, the data is closer to the mean. This one, the data is spread further apart. So this one had the smaller standard deviation, and this one had the larger standard deviation. All right, let's look at our next example on this page, example 2. Well, B. It says, which normal curve has a greater mean? So what we're looking for, where's that highest point? So it looks like B has a mean of about 12. And if we look at the highest point on A, it looks like the mean of A is approximately 15. So which one has the greater mean? A does. Now, which one has the greater standard deviation? Well, if we look at this one, everything is closer to the mean. B, it's spread further apart, so B has the greater standard deviation. All right, let's go back to the other sheet. So this is our continuous probability distribution. The mean, median, mode are all the same. They're located at the highest point on our probability distribution. One standard deviation away in either side would represent our first inflection point. And then we have 2 standard deviations and 3 standard deviations. And now we're going to talk about the empirical rule, which will give us some estimates for how much of that data would actually fall in each of these regions. So let's take a look at our empirical rule. Scroll this down. Okay, when we have a normal distribution with a mean of mu and a standard deviation of theta, you can approximate the areas under the normal curves as follows. What we say is that 68% of the data would lie between one standard deviation in either direction. So mu minus theta and mu plus theta, plus or minus 1 standard deviation. So here's our mean. Plus or minus 1 standard deviation in either direction, we have 68% of our data, which means that 34% lies to the left and 34% lies to the right. About 95% of the area lies within 2 standard deviations. So if we go 2 this way and 2 that way, from here to here, 2 one way and 2 the other, we get 95% of our data. So since we already have this 68, to find the percent here and here, what we do is we take the 95, which we know is from here to here, subtract the 68, and that's going to leave us 27% for both sides, between 1 and 2 standard deviations in a positive direction and a negative. So where we got that 13.5 was because we have both sides, is we would take that 27% and divide by 2. So it'd be 13.5%, which is the 0.135 under the curve on either side. And the last statement is that 99.7% of the area of the data lies between plus or minus 3 standard deviations. So if we went 3 this way and 3 that way, we'd get 99.7% of our data. So what would that look like? Just if we were just looking at between 2 and 3 standard deviations, what does this little part under the curve represent? Well, we do the same process. This time we take the 99.7%, subtract the 95%, and that will leave us 4.7%. When we take that 4.7% and divide it by 2, because we have the area on this side and the area on that side that has to total that 4.7, so we would divide by 2, we get 2.35%, which gives us a probability of 0.0235. Now, I've gone ahead and labeled this, given a particular example. So if we had a set of data where the mean of the data was 20 and the standard deviation was 4, what would this look like? So the first thing we would do is label the center here, curve, 20, because that's our mean. Now if we go out 4 units in either direction, that gives us 1 standard deviation. So I would count over 4, and that would be 24, count back 4, or subtract 4, and that would give us the 16. And please notice that this is happening at those inflection points on our curve. That is plus or minus 1 standard deviation. So 68% of our data is going to lie between 16 and 24. Because that is what the total area of the curve in between these two values represents. Now if I went out another standard deviation, I added 4 more, that would get me 8. A third standard deviation would get me 4 more, up to 32. If I went back 2 standard deviations, that would be subtracting 4 twice, or subtracting 8 from the 20. That gives me 12. Subtract 4 again, that gives me 3 standard deviations at 8. And now let's look at the problems that deal with this question. Okay, estimate the probability that a randomly chosen adult has an IQ that's between 85 and 145. If the mean of IQs is 100 and the standard deviation is 15. So what we would do here is we would sketch it out. So we have a mean, we're going to do our mean is 100. And so that would be the top of our curve. I'm not so good at drawing this curve, but I will always do my best. Now the inflection point on either side where it goes from curving up to curving down is where my one standard deviation is away. So, and my standard deviation for this problem is 15. So I would add 15 to the value and subtract 15 to the mean. So this is my mean. This is one standard deviation in either direction. So mean, this is mean plus a standard deviation. This is the mean minus a standard deviation. So that is one standard deviation. So if I went another standard deviation, added another, this would be at 130. This is two standard deviations plus two standard deviations. One would make it 145. That would be plus three standard deviations. Now if I went back here, that would give me 70. That would be minus 2 standard deviations from the mean. Went back one more time, that would give me 55. That would be minus 3 standard deviations from the mean. Now, I know that within 1 is 68% of my data. So this is my 34% and my 34%. I know that within 2, it is 95% of my data. When I do the 95 minus the 68 and divide by 2, I get 13.5% of the data lies under this part of the curve. And then finally, when I do 3 standard deviations, that's the 99.7. So 99.7 minus the 95 is going to leave us the 4.7, which when I divide by 2, gives me 2.35%, which is 0.0235 as a decimal. So how many standard deviations are scores from the mean? If we're going from 85 to 145. So 85 is 1 standard deviation below the mean. And the 145 is up 3 standard deviations above the mean. So it's going to go from -1 standard deviations all the way up to +3 standard deviations. And now it asks us to use the empirical rule to find the area under that curve. So to use the empirical rule to find that area, what we're going to do is we're going to add up all of these. We want everything from 85 all the way up to 145. So we're just going to add those areas under the curve there. So 0.34 and 0.34, well, that's the 68%. That's 1 standard deviation. So when we do this, we'll do the 0.68 plus, then we've got an additional 0.135 plus the 0.0235. Okay, and when we add these up, we find that the area under this curve is 0.8385. What does that mean? That means that the probability of a randomly chosen adult that would have an IQ between 85 and 145 is 0.8385. That's a fairly decently high probability, and that's what that means. Okay, let's take a look at the last example I gave you. Number 3. See, the heights of a fully grown white oak are normally distributed. So it tells us it's a normal distribution. The normal curve shown below represents this distribution. What is the mean? Well, we should be able to tell right here that the mean is 90. Estimate the standard deviation. Well, the standard deviation would be about, Let's take a look. It looks like it's switching somewhere around here. So if we drop that down, whoops, I may need the line tool. So if we drop down a perpendicular here and here, are we pretty close? Maybe 3.5, a little hard over here. So it looks like it's about 3.5 years. Okay, so what is the probability that a randomly selected white oak tree would have a height between, if we said this was 3.5, would have a height between 86.5 and 93.5. So if we wanted to know what is the probability that a randomly selected tree would have a height between 86.5 feet and 93.5 feet, well, that is just the one standard deviation. So that would be the 0.34 and the 0.34. The probability that the height is between 86.5 and 93.5 would be 0.68. Okay, because that is one standard deviation. Okay, if 3.5 is our standard deviation and we added this again, this would give us 97. So we should have another one at 97. So mine's off a little bit. It's probably closer to 3, because if I added another 3.5, it looks like we're a little bit past that, but it's not bad. It's not a bad estimate. Okay, today you have a worksheet where you're going to practice some problems regarding normal curves and using the normal curve with the empirical rule to estimate probabilities. You may work together, but let's make sure we finish these before, hopefully you'll finish before class is over. And I'll have the answers for you tomorrow.